Look around you. Almost nothing in nature exists in a state of true purity. The air, the soil, the water, and the biological materials that make up life itself are chaotic, intertwined mixtures of physically combined substances. To study matter, we first have to force it into perfectly uniform streams. Welcome to the Dr. Chem Masterclass. Today, we are going to dissect the rigorous physical chemistry required to bring order to that natural chaos. The central challenge of analytical chemistry is a delicate one. How do you isolate a single, pure molecule from an infinitely complex natural mixture? And how do you do it without destroying your target in the process? The answer lies in a principle we can call physical exploitation. Effective separation techniques do not trigger chemical reactions, and they do not alter the chemical identity of the substances involved. Instead, these methods exploit the deltas. We measure the precise differences in physical properties like particle size, their boiling point, and molecular polarity between the components of a mixture, and we use those exact margins to pull them apart. To understand how this works, we will scale up our approach. We will start with macroscopic mechanical sorting and move down to microscopic molecular interaction. Master in chemistry requires mastering separation. If you want to understand a complex system, you must first learn how to deconstruct it. Our first line of defense relies strictly on disparities in physical state and particle size. This is filtration. The core mechanism is highly mechanical. We pass a heterogeneous mixture through a porous medium to block the insoluble solids. The solid material caught in the mesh is the residue, and the liquid navigating the medium is the filtrate. To accelerate this process, chemists apply kinetic forces. Vacuum filtration uses pressure differentials, specifically a lower pressure environment in the receiving flask, to pull the filtrate through the medium at a much faster rate than gravity alone would allow. Another highly related mechanical technique is centrifugation. Rather than relying on a physical mesh size, a centrifuge uses rapid, high-speed spinning to separate substances strictly based on their varying densities. The heavier particles are driven outward, leaving the lighter liquid behind. These simple mechanical properties are highly scalable. The exact same physics used to isolate a few grams of a precipitate in a lab vacuum flask are used to purify millions of gallons of water in municipal wastewater treatment membranes. But mechanical sorting fails when we encounter miscible liquids, liquids that are completely dissolved into one another and cannot be filtered. To solve this, distillation exploits differences in volatility. We look at the specific boiling points of the distinct components in the liquid mixture. The thermodynamic mechanism is straightforward. As heat is applied, the substance with the lower boiling point absorbs enough energy to vaporize first. Those gaseous molecules travel into a condenser tube, rapidly cooling and returning to a liquid state in a separate receiving flask. When boiling points are far apart, simple distillation is enough. But for compounds with very close boiling points, we use fractional distillation, which introduces a column with theoretical plates, forcing the mixture through repeated cycles of vaporization and condensation to achieve purity.
For compounds that would degrade under high heat, vacuum distillation steps in. By lowering the atmospheric pressure inside the apparatus, we artificially lower the boiling point, allowing us to separate heat-sensitive molecules safely. This thermodynamic principle forms the backbone of global infrastructure. These powerful thermal deltas make the mass production of chemical solvents and the entirety of modern petroleum refining possible. Moving beyond physical states and temperatures, we reach a deeper level of isolation, microscopic chemical affinities and solubility. Liquid-liquid extraction is a technique that relies on two immiscible liquids, usually an aqueous phase and an organic phase that strictly refuse to mix. The partition coefficient dictates how a solute distributes between two layers based on relative polarity. Following like dissolves like, molecules migrate to the solvent with highest affinity. Mathematically, multiple small volume extractions yield a higher recovery than one massive extraction. We can also apply this to solids. Solid liquid extraction, or leaching, uses targeted solvents to strip valuable compounds directly out of a solid matrix, like plant material. Extraction is what bridges the gap between raw nature and human engineering, allowing chemists to isolate active pharmaceutical ingredients directly from complex natural flora. For the ultimate analytical separation tool, we turn to chromatography, where we exploit the most subtle differential interactions at the molecular level.
All chromatography requires two components: a stationary phase that stays fixed in place, and a mobile phase, a solvent or gas, that flows through it, carrying the sample mixture. Molecules interacting strongly with the stationary phase are slowed down, while those preferring the mobile phase are swept along quickly. This creates a unique retention time for each molecule. A chromatogram maps these times, with peak distance illustrating our resolution and selectivity. The modern toolkit ranges from paper to thin layer plates to gas chromatography and high-performance liquid chromatography. A sister technique, electrophoresis, replaces the fluid mobile phase entirely with an electric field. This forces macromolecules, like DNA or proteins, to migrate through a gel medium, separating them based on their charge and size. These advanced interactions provide the ultra-high resolution required for forensic investigations, DNA profiling, and rigorous quality control in biopharmaceuticals. We have built a complete hierarchy of physical exploitation. Filtration targets particle size. Distillation targets volatility. Extraction isolates by solubility. Chromatography separates by phase affinity. In practice, an industrial process cascades through these techniques, taking crude raw material through sequential purification steps. Chemists design integrated systems that leverage varying strengths of multiple physical properties to achieve absolute purity. We return to our initial tension. To understand the natural world, we first have to deconstruct it into its individual parts. To put the importance of this into perspective, every pure substance we use, every medicine we trust, and every scientific discovery we make depends on the ability to separate and identify components of mixtures. Separation techniques are among the most powerful tools in chemistry, transforming complex mixtures into valuable knowledge.